Hello to all. I am Dr. Manju Gupta, Department of Chemistry, St. Aloysius College, Jabalpur. Today I am going to deliver the lecture on Introduction and Basic Transition of Ultraviolet Spectroscopy. The ultraviolet region extends from 10 nanometer to 400 nanometer. 10 to 400 and the total UV region is divided into two regions. 10 to 200 nanometer is known as vacuum UV region. 200 to 400 nanometer is known as normal UV region. Whole UV region is divided into two regions. 10 to 200 nanometer is vacuum UV and 200 to 400 nanometer is normal UV region. Why the whole range is divided into two regions? Because we cannot use the same spectrophotometer for both the regions. For the vacuum UV region, when we want to record the spectrum, the whole path length should be evacuated. Otherwise, the atmospheric oxygen will start to absorb the ultraviolet light. So the main region is 200 to 400 working region of ultraviolet radiation. And if we want to record the spectrum in between 10 to 200 nanometer, we have to use vacuum ultraviolet spectrophotometer. Visible region extends from 400 to 800 nanometer. In visible region, all of us, we know there are 7 colors with Q. Visible region starts with the 400 nanometer or approximately 380 nanometer. First, the range of wavelength of violet color is from 400 to 435. From 435 to 500 indigo, 500 to 520 blue, 520 to 565 nanometer green, and 565 to 590 nanometer yellow. 590 to 625 nanometer is orange, and 625 to 780 or 800 nanometer is red. Now, why the ultraviolet and visible? These are the two different regions of electromagnetic radiations, and they are studied together because the effect of these radiations on the molecule is the same. That means both radiations, ultraviolet and visible radiations, are responsible for the electronic transition in the molecule. The difference in energy between the molecular bonding, non-bonding, and anti-bonding orbitals. These are the three main types of molecular orbitals present in any molecule or molecule. Bonding orbital, non-bonding orbital if any heteroatom or lone pair of electron is present in the molecule, and corresponding anti-bonding or high energy orbitals. The energy difference between these orbitals is from 125 to 650 kilojoule per mole. That means for the electronic excitation, we require the energy in between the 125 to 650 kilojoule per mole. Here you can see energy for 200 nanometer, from where normal UV range starts. For 200 nanometer, the corresponding energy is 600 kilojoule per mole. And for 800 nanometer, the corresponding energy is 150 kilojoule per mole. So this amount of energy is under this range, and it can be eject the electron, excite the electron from lower energy state to higher energy state. Or we can say this energy 150 kilojoule per mole to 600 kilojoule per mole corresponds or similar to the electromagnetic radiations of ultraviolet and visible region. the sample is irradiated with the broad band of UV visible radiation. Broad band, that means the whole UV visible light involve the wavelength from 200 to 800 nanometer, or the energy from 150 kilojoule to 600 kilojoule. If a particular electronic transition with respect to energy matches with the particular wavelength of UV visible light of the same energy, only in that condition it will be absorbed. When the energy from ultraviolet visible light is absorbed by a molecule, one of its electron jumps from lower energy state to higher energy state. For describing this, first we are taking the example of hydrogen molecule. In hydrogen molecule, two molecular orbitals are present. Since we know in hydrogen molecule there is one sigma bond or hydrogen-hydrogen single bond. For this sigma, these sigma electrons, there will be two molecular orbitals. One is lower energy state, sigma bonding orbital, and another is high energy state, sigma anti-bonding orbital. Lower energy state orbital is known as HOMO. HOMO means highest occupied molecular orbital. Highest occupied, that means orbitals present in lower energy states or bonding states. If more than one orbital is present, then we consider the orbital of highest energy with two electrons. That's why it is known as highest occupied molecular orbital. Orbital which is higher in energy and which is also occupied by the electrons. So in the normal state, both the electrons are present in the sigma orbital or HOMO. When the energy difference between the HOMO and LUMO or sigma and sigma antibonding orbital is 258 kilocalorie per mole. When we irradiate the molecule by UV radiations, then light of 111 nanometer matches with the amount of energy of this energy difference. That means the energy of the light with wavelength 111 nanometer is equal to 258 kilocalorie per mole. Only in this condition, hydrogen molecule can show absorption and excitation. In this condition, after the absorption of light, the two electrons which are present in the ground state, after excitation, one of the electron jumps into the higher energy state, that is sigma antibonding or LUMO state. So this is the main principle of UV transition. Always most probable transition is highest from HOMO to LUMO, from highest occupied molecular orbital to lowest unoccupied molecular orbital. We can explain this by another example, by the example of ethylene. In ethylene, carbon-carbon double bond is present and the energy difference between the two pi orbitals, pi and pi antibonding orbital, is less as compared to sigma antibonding orbital. For sigma to sigma antibonding orbital, it was 258 kilocalorie per mole, and for pi to pi antibonding orbital, 173 kilocalorie per mole. When we irradiate the molecule with UV light of 165 nanometer is absorbed by the molecule because the energy of this light corresponds to or matches to the energy difference between the pi to pi antibonding orbital. In this condition, the two electrons present in the pi orbital or HOMO orbital it can jumps from pi to pi antibonding orbital. In case molecule has more than one lower energy orbitals or more than one corresponding high energy orbitals. Only in that condition, it must be remembered that only the most probable transition will be HOMO to LUMO, from highest occupied molecular orbital to lowest unoccupied molecular orbital. When electromagnetic radiations or UV visible light is passed through a sample, some amount of radiations or some amount of light is absorbed by the substance. Remaining is transmitted by the substance. The amount of light absorbed by the substance is known as absorbance. Upon irradiation, substance may absorb different wavelengths. You can see in the graph, this is the particular UV graph. Molecule can absorb light from approximately 238 nanometer to 310 nanometer. This much amount of light, that means this range of wavelength of light can absorbed by the molecule. But a particular wavelength at which the substance shows maximum absorption, it will be recorded in the instrument or spectrophotometer. This wavelength, which has maximum absorption, is known as lambda max. So in the UV visible spectrum is plotted absorption versus wavelength. On x-axis wavelength, y-axis absorption. And a bell-shaped curve is obtained. In a particular molecule, organic molecule, 3 types of electrons can be present. If the molecule is saturated or only in the single bond, then sigma electrons. If the molecule is unsaturated, then pi electrons. And if the molecule has heteroatom or lone pair of electrons are present in the molecule, then non-bonding orbitals. On the basis of these 3 types of electrons, different energy levels can be present in the molecule. For example, for sigma electrons, ground state sigma bonding orbital and its corresponding highest energy sigma anti-bonding orbital. For pi electron, ground state pi bonding orbital and corresponding high energy state pi anti-bonding orbital. And for lone pair of electron, for non-bonding electron, there is only one energy level is there. There is no corresponding higher energy level because these electrons not participating in the bonding. On the basis of these different energy levels, we can say there are 6 types of electronic transitions are possible in the molecule. Sigma to sigma antibonding transition, pi to pi antibonding transition, N to sigma antibonding transition, N to pi antibonding transition, sigma to pi antibonding transition, and pi to sigma antibonding transition. 6 types of transitions are possible on the basis of this diagram. First type of transition is sigma to sigma antibonding transition. As the name indicates, sigma to sigma star. That means in a particular molecule when only sigma electrons are present. Sigma electrons, that means electron is present in the sigma bond. Sigma electron is excited from bonding to corresponding antibonding molecular orbital. For this transition, maximum amount of energy is required. Generally, this transition is observed with saturated molecule. Now, this transition is observed with saturated molecule, but the organic compounds in which all the valence shell electrons are involved in the formation of sigma bond, do not show absorption in normal UV region. Even the molecule has only sigma bond, only it has sigma electrons. Even after that, it do not show absorption in between 200 to 400 nanometer. For example, methane. Methane has 4CH sigma bond and can undergo sigma to sigma antibonding transition and shows absorption at 122 nanometer. It means before the range of normal UV light, 200 to 400 nanometer. Since the sigma bond is very strong, this bond is very strong. That's why for the excitation of electron, we require more amount of energy. When the amount of energy is higher, the corresponding wavelength will be lower. So for the recording of such type of transitions present in the molecule, the usual spectroscopic technique cannot be used. Since for recording the spectrum within this wavelength range, we require higher amount of energy, and when we use higher energy, the molecule or the spectrum will absorb the oxygen molecule present in the spectrum. So to study these this high energy transition, the entire path length should be evacuated. First, we have to create vacuum there. We have to remove all the atmospheric gases from the instrument. Then we can take the spectrum. That's why this part of ultraviolet region is known as vacuum UV region. These are the few examples of sigma to sigma star transition. Methane. In methane molecule, there are 4 carbon hydrogen bonds. In propane, 2 carbon-carbon sigma bonds and 8 carbon hydrogen sigma bonds. In cyclohexane, 6 carbon-carbon sigma bonds and 12 carbon hydrogen sigma bonds. All are the examples of saturated molecules and shows absorption in between 120 to 180 nanometer. This was the first kind of transition, sigma to sigma antibonding, which requires maximum amount of energy, and for recording this we require vacuum UV spectrophotometer. Second type of transition is sigma to sigma antibonding transition. Sigma to sigma antibonding transition, again the name indicates the molecule with sigma bonds, pi bonds. Pi bonds are present in the unsaturated molecules having double or triple bond. Pi electrons is excited from bonding to corresponding antibonding orbital. Energy required for this transition is less as compared to sigma antibonding transition and N to sigma antibonding transition. Unsaturated molecules undergo pi to pi antibonding transition. And for recording this type of transition, we can use normal ultraviolet or ultraviolet spectrophotometer. These are the examples of pi to pi antibonding transition. In ethene, there is only one double bond. The lambda max for ethene is 170 to 190 nanometer for alkenes. For conjugated alkene line 1,3-butadiene, for conjugated alkenes, the range is 190 to 220 nanometer. As the number of conjugated double bonds increase in the alkenes, if 2 or more double bonds present in the conjugation, the value of lambda max will increase by 10 to 20 for each conjugated double bond. Other than alkenes, in the molecules which are having double or triple bond, pi to pi antibonding transitions are possible. Like carbonyl compounds, in case of acetone, C double bond O group is there. So pi to pi antibonding transition in acetone is observed at 180 nanometer. Other than this, molecules having triple bond, alkynes, carbon nitrogen triple bond, nitriles, aromatic compounds, and some other molecules which are having double or triple bond can show pi to pi antibonding transition. Third type of transition is N to sigma antibonding transition. N to sigma antibonding transition name indicates that the molecule with sigma electrons as well as non-bonding electron. Non-bonding electrons can be present with heteroatom in the form of lone pair of electron. When these lone pair of electrons are excited from non-bonding electrons to higher energy sigma orbital or sigma antibonding orbital, it is N to sigma antibonding transition. Simple saturated compounds containing atoms with lone pair of electrons like oxygen, nitrogen, sulfur and halogens are undergo N to sigma antibonding transition. This transition requires less energy than sigma to sigma antibonding transition. And the lambda max for these type of compounds in the range of 150 to 240 nanometers. Alkyl halide, alcohols and amines shows the N to pi antibonding transition. In saturated alkyl halide with the alkyl group, any halogen can be there. Fluorine, chlorine, bromine, iodine. The electronegativity of halogens from fluorine to iodine decreases. The energy required for transition decrease with increase in size or decrease in electronegativity. The energy required for transition decrease with increase in electronegativity of halogen atom. When the electronegativity is higher, it is difficult to excite the electron and it requires higher energy and shows absorption at lower wavelength. That's why methyl chloride shows absorption at 169 nanometer. Whereas in methyl iodide is less electronegative as compared to chlorine. When it is less electronegative, the electrons can be easily excited to higher energy level. It requires less amount of energy and shows absorption at higher wavelength. In alcohols and amines, as the hydrogen bonding increases, value of lambda max shifted to shorter wavelength. So, for the detection of electronegativity or for the study of hydrogen bonding, N to sigma antibonding transition can be main transition. Next transition is N to pi antibonding transition. In case of N to sigma antibonding transition, molecule with sigma electrons and non-bonding electrons. In this type of transition, in a molecule, pi orbitals are there, pi electrons are there, as well as heteroatom or the non-bonding electrons are also present. An electron present in the non-bonding orbital can absorb the energy and promote it to high energy pi antibonding orbitals. Unsaturated compounds containing heteroatom undergo such type of transition like C double bond O, C double bond N, C double bond S4, where oxygen, nitrogen, sulfur, these are the heteroatoms having lone pair of electrons. This transition requires minimum energy and show absorption at longer wavelength around 300. When requires less amount of energy, shows absorption at higher wavelength, since energy and wavelength both are inversely related. These are the four main transitions of organic molecules which are practically possible. In case of carbonyl compound, here we are taking the example of acetone. In between carbon and oxygen, pi bond is there, and on oxygen, lone pair of electrons are also present. So in carbonyl compounds, both the transitions are possible. From double bond, pi to pi antibonding transition, from lone pair of electron to corresponding pi antibonding electron, from non-bonding to pi antibonding orbital is N to pi antibonding transition. So in case of carbonyl compound, always we observed two bands. One is of higher energy observed at lower wavelength because of pi to pi antibonding transition. Another is of lower energy and observed at higher wavelength is N to pi antibonding transition. Out of these two transitions, sigma to sigma electronic transitions are allowed, and pi to pi antibonding electronic transitions are allowed, and N to pi electronic transitions are forbidden. That means the probability of the transition from non-bonding electron to pi antibonding electron is less as compared to pi antibonding orbital. These are the two main transitions which are generally studied in the UV range. So these are four main transitions. Other than this, sigma to pi antibonding and pi to sigma antibonding, these two transitions are also possible on the basis of this diagram. Sigma to pi antibonding and pi to sigma antibonding. But these transitions are only theoretically possible. Practically, these transitions are not possible, and these are known as forbidden transitions. In ultraviolet visible spectroscopy, mainly two transitions are recorded because of N to pi antibonding and pi to pi antibonding transitions. These two transitions can be recorded by normal ultraviolet visible spectrophotometer. Ultraviolet visible spectroscopy mainly used for the compounds containing unsaturation or carbonyl compound. Unsaturation, that means pi to pi antibonding transition, when the electrons present in the, this is the HOMO of any alkene, and this is the LUMO of alkene. Excitation of electron from HOMO to LUMO or from pi to pi antibonding. Similarly, in the case of carbonyl compounds, pi to pi antibonding because of carbon double bond oxygen, and N to pi antibonding. Both the transitions are possible. So in case of UV visible spectroscopy, these two transitions are mainly recorded. And for both the compounds, alkenes as well as carbonyl compounds, as the unsaturation or conjugated double bonds increases, the molecule, the lambda max for the molecule shifted towards the higher wavelength. Thanks, sir.